with the neuromorphic computing. And then now I will spend some time to do a 3D LAN. It's not too difficult if you know what we have discussed before. Okay, any questions?
This is a flash memory architecture.
This is flash memory LAN type. So there are two types of flash memory, but nowadays only the LAN is really important, earning a lot of money. This is LAN type. There is also NOR type, but we don't discuss here. Okay, so I'm going to erase this one. LAN type because they're all in this string. Yeah. Is that okay?
Yes, thank you.
So this is LAN type in terms of the architecture, but flash memory is the same. They all use this basic unit cell through programming in this way. But more than that, if you say NOR type, we can also do hot carrier injection, not really depends on the tunneling. Right? We apply very high voltage, you get hot carrier, energetic electron is going to inject into the charge storage layer. Right? But we don't discuss this here much. Okay. Now, if you understand this 2D LAN, then there's no problem in understand the 3D LAN. This from this paper is a very good picture. 2D LAN, you put it in this way, right? So let's look at this carefully. This is the channel, the blue one. And then you can charge trap layer. Basically, is the oxide trapping, oxide storage oxide, right? And then on top is just the control gate. Again, remember we have the select line for this whole string. Well, how do you make it 3D? Just pictorially, you just rotate it and then you become 3D, right? Nothing wrong with this one. The only problem is how are you going to make this? It's impossible, right? So people come up with an idea. It is that let's make it symmetrical. So in a real 3D LAN, it's the same, but this is symmetrical. So how does it work? This cut into it. It has a center channel all the way to here. This is the channel, just like the blue one. Okay. And then you have this charge storage layer, just like this one. And then you have the poly, right? So how do you grow this? What you do is that you need to form a multi-layer. This one you need to first, you have the poly, you deposit all the poly, and then isolation. Between the gate, you need isolation, poly isolation. You do it for 128 layers. That's why the deposition machine is very important now. In the past, a fab is the lithography. The lithography guy is the most powerful because they are the slowest one. You know, this is the real world. Who are working slow, who are not productive, who has more say. And that is the same at the fab. Because lithography throughput is very slow, right? So all the VP manager put attention to them, and they're very expensive. You need to scale them. But nowadays, because of the 3D LAN, you actually need to buy a lot of deposition tools because you know deposit 128 layers, and including the isolation, it means 256 layers. That takes very long time. So they need to buy many deposition tools. And also etching. Once you deposit, they etch a really, really high aspect ratio hole. So this is again important. And then they fill up with the oxide, fill up with this channel. And then you get this string like this, array of string. And then you pattern on the top, right? So now you have the 3D LAN. Now, if you look vertically, actually, it is more natural to us. Isn't that this is the string? In the past, you keep thinking this lay on the plane. No, now actually it's just vertical, right? So these are all the control gates. Here, just a better look at what it is, right? It shows us how this pillar looks like, core field. Polysilicon, that this one is important. This is the channel. You cannot deposit crystalline silicon easily if it is not epitaxial growth, right? Because you need to fill up the trench, usually it's polysilicon. So this is the channel. And then you have a tunnel oxide. And then you have this storage layer, the pink one. And then you have the blocking oxide. And then this is the control gate. So you see, I have a plane of control gate. Every time I turn this one, let's say 20 volt, it applies to the plane, all the pillar cutting with the plane. Any question about this one? I think there's not much I can say. I'm not going to talk about the fabrication process. So if you understand this figure, that would be good. If anything not clear, please let me know.
This is inaccurate, right? There should be separation on the planes, on the red planes.
It is accurate. No, you are talking about between these two planes or within the plane? What separation?
Within the plane.
No, within the plane, they are connected. So this is like when I here, right? When I select this word line, all the transistor at every pillar got selected. But how do I only select this one for reading? Then it depends on the bit line. For example, I only put this one to high. And then I also have the bottom one, and not bit 9, this is the bit 9, and then I have another bit 9 selector. This one and this one will turn it on, and this one put high, then only this one is going to read. Although all of them get 10 volt.
Okay, so you have the selector, okay.
You do need to, yes.
Okay, got it.
The XYZ, right? The past we only use XY to adjust a crossbar. Now it's XYZ. So this is X, this is Y, and the plane is Z. And then only one of them is selected. Okay, and this is in your laptop already, right? In your iPhone. This is really amazing. If you look at the history of flash memory, right, or if you had chance to visit Western Digital, you used to go there, right, as their customer, right, they will put on the banner, congratulations for the 1X node. It means 10, maybe 90 nanometer, they don't disclose production. And then 1Y, maybe 15 nanometer. And then 1Z, maybe 14 nanometer. I don't know, that's a secret. But the point is everything stopped there. That is the planar. They finish all the scaling. You cannot make it smaller anymore for 2D. But once they go to 3D, everything got relaxed. And then the Moore's law again goes up. And that's why now it's so cheap, right? The flash memory. But now they are hitting another roadblock. They already make this maybe now trying to have 256 layer. They cannot do too much because this etching is very, very difficult, very high aspect ratio. Okay. You remember when I do the etching, I need to make the width at the top and the bottom to have the same diameter, right? I cannot have something.
Yeah, I mean, how do they do that? Do you have any idea?
Oh, just read the paper. I don't know exactly the recipe, but you need some special recipe, right? So in MEMS, we have something called Brosh edge. If you heard about that, Brosh edge. But that is more for relative larger, and also they don't care about this so-called scallop. Brosh edge is something you can get very high aspect ratio, but it's not very clean here. But this one, we're talking about nanometer. Right? Maybe Bosch edge can also do that, maybe 10 nanometer or even smaller, right? So they have some special, they actually, it's a very good chemistry control on first the temperature, right? The wafer temperature is important, the etching chemistry and passivation. When you etch something, the chem is going to depassivate, to passivate and prevent further etching. You need to go through all this process to make it nice, then it works well, right? But Samsung is very good at this. Western Digital don't do this. They partner with Toshiba. Basically, Western Digital is more like a fabless. However, they have very close control on the process. All the fab are in Japan. Toshiba did that. Okay, Western Digital, of course, what I'm talking about is the previous SanDisk, right? Western Digital bought a SanDisk. Okay, any questions? If no, let's go to the last topic, not included in the exam, right? If you're interested, I encourage you to take EE 225. I hope that I can offer it again next year in fall. That's my plan for